opportunity of being here. And even when my talk, I don't have any stochastic system, but all deterministic. But, well, maybe in the future I will make something on stochastic. Well, this is a joint work with Laura Aragón and Pablo Lotito. Laura Aragón is from my university in Rosario, and Pablo Lotito from University of the Center of the Buenos Aires province. Well, the talk will be focused in the analytical aspects of the problem. We would like to prove that for this particular problem, all the theory of the dynamic programming works well. So, and then we will show some preliminary numerical approach where we have not studied too deeply already yet, but I will show some developing ideas that we want to work. Maybe someone has some advice to me. So this is our problem. We consider a dynamical system that evolves on a bounded domain, which is, we ask for omega that have a regular enough frontier. And we have a control alpha that belongs to this set, is the set of controls from R positive reals to 0, 1 that satisfies this system. That should be see as interpreted as the integral, in the integral sense. And actually this alpha is like an artificial control. The real control is the function u. And why we state this like this? Well, in fact, first of all, that this presentation generalizes the monotone control problem. That is the case when this alpha is 0, identically 0. And well, the monotone control problem was deeply studied in the early 80s by Baron and Jensen in the finite horizon case, and there is a nice presentation of the infinite horizon case in the book by Bart and Capuzzo Dolcetta. And the idea is that the monotone control problem is associated to some problems where you consume some non-renewable resource, and in this presentation we allow to that maybe the resource has some properties can be renewable. So it's not only decreasing control. So, well, here the usual hypothesis: if and g are bounded Lipschitz continuous functions, and well, we make some additional assumptions to guarantee that the system remains in omega, and well, and the control remains in 0, 1. This maybe one of them for instance, you must ask that g at 0 must be non-negative, and well, at the frontier of omega, this f must point inward, at least for some admissible control. So we want to study the properties of this system, this problem. We have two optimization criteria. We are interested in this one, is the problem with long-range average cost criterion, where the functional that we must minimize is this, the lim sub 1t tends to infinity of this integral. And, well, it's well known in literature that for the classic problems, this problem can be approximate, but the infinite horizon problem with discount factor lambda, and if we study the asymptotic behavior of this problem when lambda tends to 0, then we can obtain a solution of this problem. So the idea is to prove that in this case that works too. So we first study the infinite horizon problem. Now we must make some assumption. The weak controllability property is, the idea of this property is that if we take two initial points, and some control to starting at this one, there is another control starting here that can reach the trajectory of the another one. And with at some times that are not far too far. So if you take, for instance, this tau is 0, you have the usual controllability property. And actually, also this, as I write it here, is maybe too strong. What I really need is that I don't read exactly for all the controls, but I need that for all positive lambda and for all epsilon optimal control. Alpha for the for V lambda of yes. If I just for this epsilon optimal control, I can reach with this one. That's enough for our purpose. Why is that? That I have to maybe have to get a weaker controllability property. Is that our controls maybe just can decrease. If you take the monotone control problem where the G is 0, you can only decrease. So if suppose that a constant control is admissible and you start a little below that, you never will reach the null. So maybe I can't ask for all the controls, but only for the epsilon optimal controls. So well.
But then the condition should depend on G.
Yes.
There is no G.
No. No, in the assumption, no. Well, the assumption is make in the system is usual to you have not that is right. No, but I have to put this here. I remember. You can see that these two controls will satisfy the previous dynamics, so it's implicitly there, the G, as the F is implicitly here. So, well, with this assumption, well, we can prove this proposition. For any lambda non-negative, well, positive lambda, the value of the value of function is continuous, is non-increasing in the variable a, and is bounded by this bound, where this ML is the bound of L. The value function satisfies this dynamical programming principle. And under the weak controllability property, the family of values functions with lambda positive is equicontinuous. It will be very useful for using Arcela theorem. So, well, we'll remember the definition of constraint viscosity solutions. A function is a constraint viscosity solution of this equation in the closed set. If it's a viscosity solution in the interior, and a constraint viscosity super solution in the whole set. So we have a subsolution is that for all phi smooth in Rn, this inequality satisfies at any local maximum point of the difference, and now for the super solution, this inequality satisfies at any local minimum point in the closed set. So, what we have? One, we can prove that the values function b lambda is the constraint viscosity solution in the bounded set, in the previous sense of this Hamilton-Jacobi-Bellman equation. This is actually, well, we can see as a variation inequality. It's actually a complementarity problem. And this is almost the same as the Hamilton-Jacobi-Bellman variation inequality for the usual monotone control problem. Now we have in the Hamiltonian, we have this part of that depends on G. Well, we also could prove a comparison principle that if we have a super solution and sub-solutions, the sub-solution must be lower than the super solution. Well, actually, this is the most difficult part of the proof. That, well, takes a lot of work. Well, as an easy corollary, the value function will be the unique constraint viscosity solution in this set of this variational inequality, Hamilton-Jacobi-Bellman variational inequality. So, we have now good properties for the infinite horizon problem. Now, we have to study asymptotic behavior when lambda tends to 0. So, well, it can be proved, it's easy to prove that there exists some real number, mu, where when lambda tends to 0, lambda times the value function tends to mu uniformly in the set. And this mu will be the solution of this problem. So if what we prove here is that that mu is really a constant. Well, if you see here, well, a priori this value depends on x on a, but well, actually it does not depend. That is the same what happens in the usual average cost criterion when the constants are all the measurable functions, for instance. So we have proved that this is actually this is a constant. And well, for any function v in this set, it is like it's like similar to a upper limit of sets with where we take the set of this be random minus some fixed point, and you make lambda tend to 0. And for any function there, the pair mu u, this is v, mu v, will be a constrained viscosity solution. If this is is omega bar of this variational equality. Well, look that here, this is just a constant. So it's you may expect that there will be no uniqueness of solution because well, the equation just involves derivatives. So, but it's not only that there are either no uniqueness but constant. It's true that if you get a solution v plus a constant will be a solution, but not only that. There could be others. So, well, that's a good result for us. So that completes the part of the study of the analytical aspects. And now I want to talk a bit on the numerical approach. Well, the usual thing to do is make a discretization procedure with linear finite elements. So we have a triangulation of omega and with diameter k. We discretize, get a partition of the 0, 1, and consider linear finite elements. So our functions will be some function in this set that is fully determined by the values in the nodes. So we can think that a function as a vector in RLM. So, well, these are discretized problems. Discretization of the Hamilton-Jacobi-Bellman equation for both problems, the infinite horizon and the average cost criterion. So, what says that? Look, for instance, if you start at 0 here, then at the next step you cannot go down. So it will be just the only thing to do is to go with the dynamics. And if you are not at 0, well, maybe you go on the dynamics and maybe you stay at the same value of the previous value. And in this case, and at this segment, the derivative will be 0 in the second variable. So that's the idea of the discretization, and it's similar to the another one. Well, and now what we have to see that for this discretization, there is a similar behavior for the continuous part. So, well, what we can obtain is that, well, we have to solve some, for this, a fixed problem. And here we don't have a exactly fixed problem, but because we have to find a couple. Here, mu is also an unknown. And well, this is not a contractive operator, so the problem is a little bit harder. So, but the first one, we can prove that not the operator, but some power. This m is the amount of points in the interval 0, 1. This power is contractive. So the problem has a unique solution and verifies this bound. And what we can prove is that for the another problem, there is at most one mu such that the problem has a solution. If you assume that given some point, fixed point, there is a constant such that this function is bounded, then we can prove that any w mu k for this mu, that is this the one that has a solution. If we can prove that this is the limit of these functions and w is in this set, well, then this will be a solution of the problem. Again, it's a good result, but well, what we can do for that? This well, we can say, well, take a small lambda and make a fixed point algorithm, but that is not good enough because, well, at first, just the power is a contractive operator, so as m increase, we have to make lots of iterations to get a little contraction. And when the contraction state is the order of 1 minus h lambda. So if you take small lambda, this will be so slow. And this is so what. So, well, what's the idea that we have to work next? We want to consider some policies with this is but the policies are this, see, from this set in 0, 1. And we associate to a policy the Markov chain, which is associated to discretization of this way. If the policy is 0, we have a deterministic transition. It's just taking the previous one. And if it's 1, the transition probability is given by the barycentric coordinates. When I here put the dynamics, and we can, since the finite elements are linear, we can write this on this way. And well, this is unusual interpretations, and the idea is then to construct some policy iteration algorithm and obtain estimates. We don't know if we can do it, but well, that's all. Well, for finish, I want to make some workshop announcement. It's the 5th Latin America workshop on optimization and control that we will hold on Tandil, Argentina, from July 5th to 7th. This is the web page. Well, this is a workshop that made by young researchers in Latin America. The first one was in Quito, organized by Juan Carlos de los Reyes, who is here. Then I organized the second in Rosario. There was one in Valparaiso, and the last one in Lima. Well, next is in Tandil, and maybe the next could be in Rio.
I think Curitiba was decided.
Oh, Curitiba.
Okay,
Well,
thank you, Lisandro, for your talk. Maybe we have time for a short question or comment.